Hi and welcome, and once again I have pushed the boat out. Do you see what I've done here with my crazy graphic? No? Well, that's a hat for a degree, because we are dealing with polynomials of a higher degree. Hold on one moment while I laugh. Nope, it's passed as much as it wasn't funny. Okay, so if those of you who are following along with the Cambridge Essentials textbooks, well, good news. We're on 4F. And that's the work that my guys, who, if you are unlucky enough to be taught by me, are going to be asked to do. So here's a recap. We have today been dealing with polynomials of degree 2. And if you remember, degree 2 is a quadratic. And last lesson or last video, degree 3, which is a cubic. Well, now it's time to move on to our next set of polynomials. That's degree 4, and they are known as quartics. So anything to the power of 4 is a quartic. So we have had a collection of tools allowing us to factorize cubics and quadratics. One of the things I need you to remember over and over and over again is, and let's deal with the cubic here, when we are factorizing using the rational root theorem or polynomial division or synthetic division, we are actually trying to find our x-axis crossing points. Why are these important to me? Well, because we can then use this information to write our cubic as a product of linear functions. And when you say product of linear functions, you're going to go, what do you mean? Well, if I had this as x plus 3, x minus 1, and x minus 4, for example, well, this is minus 3, this is 1, and this is 4. Well, using this information, if I was to multiply it out, I would end up with a cubic of some description. Well, we don't at this moment in time know whether this is the final cubic, because the one thing we haven't got in this information is information about a dilation. But factorizing allows us to write something in this form, which then we can expand and write in terms of the general equation. All right, so factorizing is really important. Not all times will we be given the cubic and asked to factorize it in this way. Lots of times we'll be given graphs, and you've got to fit the information you've been given to a certain number of rules. So what we're going to do now is look at the general form for quartics, and obviously the first one here is x to the power of 4. Now, for those of you who don't know or aren't using it, I can seriously recommend desmos.com to help you draw these sketches and to visualize what's going on. It's a fabulous piece of software, and no, they are not sponsoring my videos, but if they want to send me a free hat, I'm more than happy. But x to the power of 4, great graph. First things first, it's of the same family as the quadratic. Yes, x squared. All right. This, however, actually, if you look at it, is much closer to the y-axis than x to the squared or x squared is, right? X squared would actually be going something like that, and I mean literally something like that. We notice they share the same minimum point in this situation, centered around the origin. We said it was symmetrical around that line there, which is the y-axis, or the line x equals 0. And it is a pretty funky graph. Okay, pretty funky. That's important for us to remember. Then when we start messing with the x to the 4 by adding additional terms, then we see the graph starts to change shape. Again, this particular graph is symmetrical around the center, right? So it has an axis of symmetry. And we notice we have 1, 2, and 3 crossing points. We also have 1, 2, and 3 turning points. Now, the turning points here, and we come to this later on in differentiation in a later topic, but we know our turning points have a gradient of equal to 0, right? So just when we were drawing a tangent at that point, we would know for each of these that our gradient is equal to 0. But it's a fairly funky graph. How many turning points do we have? We have 3. Now let's just have a quick check here. When we had a quadratic, how many turning points did we have? So that was x to the squared, and we had 1 turning point. For our cubic, we had x to the power of 3, and there were 2 turning points. And so it makes sense here that our x to the power of 4 should have, as a maximum, 3 turning points. Now again, I say as a maximum here, remember with the cubic, this was just one form of the cubic. We have the general cubic function, which does that there, and as such, then it will only have 1 turning point. And in some cases, it doesn't even have a turning point at all. If you want to know why, go back to the cubics video. But in this situation, we need to realize that a quartic can have up to 3 turning points. Then we get even more exciting. Now, if you remember from the idea when we have x plus 1 squared, for example, when we're dealing with a quadratic, then what we know is that that has a repeated root just touching there at the number 1. Right? So anything with this squared notation means that it has a root that just touches the x-axis. If we notice here, what do we see? Well, we've in fact got 2 of them. Now that sort of makes sense, because if I was going to multiply out these brackets, x plus 2 squared, then I would be looking at my final function to start with x to the power of 4. So that's good. But the particular way this is written suggests that it now has 2 repeated roots. One around the value of 1, and there it is, and one around the value of -2. Now, in the same way as we've done previously, we can find our y-axis intercept by putting our x value equal to 0. And if we look and draw a line straight down through the middle, we are lucky, and again, it has our axis of symmetry, which is roughly around minus 0.5. How would we know that? Well, if I do -2 plus 1 and halve it, and why -2? Well, that's where the first repeated root is, and 1 is where our second repeated root is. And then divide it by 2, we in fact get -0.5. Let's just check the important information. It has 1, 2, 3 turning points. It absolutely does. And in this situation, it just touches the x-axis in 2 places. So this type of information is actually really important. And let's take it to the bank, as I say here, the last particular style of graph. Now we notice we've got a cubic and 1 linear factor. Well, if we look at our cubic, can you see where it is? Just making this slightly smaller so I can fit the whole graph in. And there we go. There is my cubic at 1. So yes, we'd be looking at here at 1. So there is my cubic, and my other factor is at -2. How many turning points does it have? 1, 2 in this case. So much like all of the other graphs, we need to be aware that the number of turning points, the number of axis intercepts vary depending on the actual function we're using. So important things to know. And this is pretty much the end of this lesson, ladies and gentlemen. My apologies, it's not a long one. So, important things to know. Quartic functions can have 0, 1, 2, 3, or 4 axis intercepts. Let's just check. So 0 would be effectively above the line. All right, that's a really bad example, drawing at least, but general idea, that's 0. And then we have 1. How many would it be 1? Well, this is the one that's interestingly tricking me, or tricked me earlier. So that's where it just touches the x-axis. So that's 1. How would it have 2? Well, we've already seen an example there of when it just touches in 2 places there and there. So that's 2. 3. 3. Oh, we've done that one before. 1, 2, 3. So there is 1, 2, 3. And much the same way, 1, 2, 3, 4. So there are 0, 1, 2, 3, and 4 axis intercepts, and it can have 1, 2, or 3 stationary points. Now again, 1, 2, 3 stationary points there, 1 stationary point there, 2 stationary points. How on earth would we end up with 2 stationary points? Well, again, if you remember from the graph we looked at earlier, the one that went like that, so there's 1 and 2. Always important to know the shape of the graphs. I say time and time again, when you end up with VCE questions that are asking you particular information about a shape or a curve, it is always a really, really good idea to draw a diagram. I can't express enough how a quick sketch can actually save you many, many hours of heartache. All right, so this was a quick jaunt through polynomials of a higher degree. Thanks very much for watching. I look forward to seeing you next time. Hi, and thanks very much for watching this, another video by me, the Maths Guru. If you would like to see more videos, why not subscribe and get regular updates? Otherwise, hey, click on the left and watch our next video. Okay, thanks very much. Have a good day.